In this video, we'll talk about finding the arc length of various polar curves. So now I want to expand from area to talk about arc length also in this polar coordinate format. Because again, some functions are a lot easier to look at in polar coordinates, and so if we can find a formula in polar coordinates to find arc length, we can use this method as well. What was our formula for doing this in terms of a parametric equation? Well, for a parametric equation, we had that the arc length was the integral from a to b, square root x prime of t squared plus y prime of t squared dt. That was our formula for a parametric equation to find the length of the curve. How can we use this to get a formula for polar coordinates? Well, if I'm doing this in polar coordinates, I want my integral to be in theta. That's my independent variable, so I should have everything be in theta to work this out. So what can I do? Well, I have formulas for x and y in terms of r and theta. I can use my function r is f of theta, plug all that in, and then just see how it works out. Maybe that gives me a formula that I can use. So the point is we have x and y in terms of r and theta. So what I can do is I can set r to be f of theta, plug all this in, and hope that gives me a nice formula that I can use. Let's see how this works out. So the point here is I want to figure out what does this expression here look like. X prime of t squared plus y prime of t squared all square root. That's what's got to go in my integral. So what do I know? Well, I know that x of theta, everything's going to go to thetas now, is r cosine theta, which is f of theta cosine theta, which then means x prime of theta should be f prime of theta times cosine theta minus f of theta sine of theta by the product rule. I can do the same thing for y. So y of theta is going to be f of theta sine of theta. I can differentiate this as well. Y prime of theta is going to be f prime of theta sine theta plus f of theta cosine theta. I then need to square each of these. Is going to be 3 terms for each. Write all this out and see what happens. So x prime of theta squared is going to be f prime of theta squared cosine squared theta minus 2 f prime of theta f of theta cosine theta sine theta, and then plus an f of theta squared sine squared of theta. We then have that y prime of theta squared is going to be f prime of theta squared sine squared of theta plus 2 f prime of theta f of theta cosine theta sine theta plus an f of theta squared cosine squared of theta. Now if I go to add these up, what happens? Well, I notice this term here is the same as this term, but with a minus sign, so they'll both cancel out. I then see that with f prime theta squared, I have a cosine squared plus a sine squared. That'll add to 1. On the f of theta squared, I have the exact same thing, sine squared plus cosine squared. Those also add to 1. So my resulting formula here is that x prime of theta squared plus y prime of theta squared is equal to f prime of theta squared plus f of theta squared. And this is the fact we need to put our formulas together for doing arc length in polar coordinates. So assume that f prime is continuous on the interval from a to b, and the arc length s of the curve r goes up of theta is given by s equals the integral from alpha up to beta of the square root of f of theta squared plus f prime of theta squared d theta. Again, because this expression in here was x prime of theta squared plus y prime of theta squared, this just came directly from our formula for doing arc length in parametric equations. Another point to note here, because again it's complicated things under a square root, this might be impossible to work out by hand. And you might need numerical approximations to actually get the value of this integral if this is the case. So as an example to wrap this up, find the length of one petal of the curve r equals sine of 5 theta. This is our same curve from before, but now I want to do the length of one petal and not the area inside. So we know that one petal goes from 0 to pi over 5 in terms of theta. That becomes the bounds of our integral here. So then what are we integrating? Well, f of theta is sine of 5 theta, which means f prime of theta is 5 cosine of 5 theta. And now we can just plug into our formula and see what we get. So our arc length here is the integral from 0 to pi over 5, square root of f of theta squared, so sine squared of 5 theta, plus f prime squared, 25 cosine squared of 5 theta d theta. You can simplify this a little bit by pairing the sine squared with one of the cosine squareds to add to 1 to give you the integral from 0 to pi over 5, square root of 1 plus 24 cosine squared of 5 theta. And there's no way really to work this one out by hand. We're stuck at this point. We can use numerical approximation to get this arc length. And if we do that, we get that this s is approximately equal to 2.101. That's how we do arc length using polar coordinates. The formula is on the same level as the one we have in parametric equations, but because one's a derivative and one's not, it's going to be a lot less likely to work it out by hand unless you have a really nice function to work with here. It's important to be able to know how to set up these integrals, how to know how they work, as well as how to be able to evaluate them should they be something you can actually evaluate to figure out the arc length of these polar curves.